The kidneys have many jobs, but their main job is to filter the blood and make urine. So to give a basic overview, you have blood comes into the kidney. So this is dirty blood goes into the kidney. The kidney sorts the molecules in the blood. For each molecule, the kidney either decides that it's a good molecule you want to keep, and so it will come out in the clean blood. Or it will decide that it's a waste molecule and you want to get rid of, and it will come out in the urine. So the urine and the clean blood together add up to what was in the dirty blood. Everything in the dirty blood, as it goes through the kidney, will either end up in the urine or end up in the clean blood. So now we can look at some more detail of how this happens. This is a nephron. A nephron is the functional unit of the kidney. This is what's actually doing the filtering. And these are tiny. They are microscopic, and you have millions of them. The nephron has blood flow in, so the blood would be coming in this way. This would be the dirty blood coming in. And this vessel that it enters through is called the afferent arteriole. So dirty blood comes in through the afferent arteriole. Then it flows through the glomerulus. The glomerulus is a ball of capillaries, so it is a special type of capillary. It's only found in the kidney. And remember, capillaries are permeable. So they have holes so stuff can flow in and out. So this is where you're going to have filtration occur. You will have anything small enough to fit through the holes in the glomerulus will leave the blood. Notice at this point, we're not necessarily sorting if it's a good molecule you want to keep or a waste you want to get rid of. We are sorting by size. So right here, you get all those small molecules. And this is called filtrate. So filtrate is the small molecules that leave the blood. And notice that you have a structure surrounding this capillary. This is Bowman's capsule. It surrounds the glomerulus and catches the filtrate. So all along here, you would have small molecules coming out, and they're all being caught by that capsule. Okay, then this is the efferent arteriole. This is the blood minus its small molecules. So this is what's left of the blood after you have removed the small molecules, and it flows out this way. So the efferent arteriole is the blood after it has gone through the glomerulus and you've taken the small molecules out. Okay, and then we have the proximal convoluted tubule. So we'll just abbreviate this PCT. This stands for proximal convoluted tubule. The filtrate flows into here. And once it flows into here, it is now called tubular fluid. So it's the same molecules, we just changed the name of it. Then that tubular fluid flows through the loop of Henle. So the tubular fluid goes on this direction. It goes down, it goes around, it goes back up. Then we get to the distal convoluted tubule. So we'll just abbreviate that DCT. That's distal convoluted tubule. The tubular fluid flows through here. Then we get to the collecting tubule, is this little stump right here. And then this is the collecting duct. So you're going this way. Once you get down to the end of the collecting duct, then the tubular fluid is called urine. So you start off, you have filtrate, is the small molecules you remove from the blood. That filtrate flows through the rest of the nephron, the proximal convoluted tubule, the loop of Henle, the distal convoluted tubule, collecting duct. As it's flowing through these areas, so here from proximal convoluted tubule all the way to here, you are making adjustments to it. You are doing reabsorption. So some of those small molecules that came out while you were in the glomerulus, you actually want to keep. So you move molecules you want to keep back to the blood. And you do secretion. This is where there's large molecules still in the blood that are waste, and you want to get rid of those. So you move waste molecules to the tubular fluid. So step one is filtration. Then you do reabsorption and secretion. And after you've done these three processes, then you have urine, which is the parts of the blood that you want to get rid of. Here's another picture just to look at those processes again with a little more detail. So we have, here is the afferent arteriole. Remember, this is the dirty blood enters. Here is the glomerulus. This is where you do filtration. So small molecules are pushed out. Remember, filtration, you're just going by size, not by what's good or bad. Then here is the efferent arterial. This is the blood after filtration. Okay, then that blood continues on to this blood vessel, which is called the peritubular capillary. So when we're doing reabsorption and secretion with the proximal convoluted tubule and the distal convoluted tubule, we are doing that with the peritubular capillary. So you would have your filtrate right here. That filtrate would flow into the proximal convoluted tubule, and then we would call it tubular fluid. So the tubular fluid and the blood, actually, let's say the tubular fluid in the proximal convoluted tubule and distal convoluted tubule exchanges with the blood in the peritubular capillary. Okay, then follow the blood. So here's your blood flow like this, like this. Your blood comes around like this, and then the blood goes to exchange with the loop. This part of the blood vessel down here is called the vasa recta. So the blood in the vasa recta exchanges with the fluid in the loop. Okay, so you have kind of two different fluids flowing here. You have dirty blood comes in right here through the afferent arterial. It goes into the glomerulus. Then you sort that dirty blood into two piles. The small molecules come out and become filtrate. The large molecules stay in the blood and go in the efferent arterial. The filtrate enters the proximal convoluted tubule, and now we call it tubular fluid. The blood flows into the peritubular capillary. So here we will have reabsorption and secretion between the blood in the peritubular capillary and the tubular fluid in the proximal convoluted tubule. Then the blood goes on to the distal convoluted tubule. It does reabsorption and secretion there. Then the blood flows around and it comes down here to the loop. And then the blood's going to exchange with the fluid in the loop. Then the blood goes on out and rejoins the rest of your circulation. The fluid goes from the proximal convoluted tubule down here to the loop, exchanges with the vasa recta, then comes back up to the distal convoluted tubule, exchanges with the peritubular capillary. Then the fluid goes into the collecting tubule, collecting duct, it goes down this way, and what you get at the end here is urine. So there is an overview of how you filter the blood and make urine. I know this is a lot, but we're going to go through it in more detail, piece by piece, and it will start to make sense. This is just your overview of it. Okay, let's look in some more detail at the process of filtration. So right now we are just focusing on filtration and how that process works. So again, you have your afferent arterial. This is the dirty blood. It comes in like this, and it goes into the glomerulus. Now we are going to push small molecules out. So remember, the glomerulus is a capillary, and capillaries are permeable. They have holes. And you actually have what's called a filtration membrane on the glomerulus. Think of it like a sieve. Remember when you were a little kid and you played in the sandbox and you had a sieve and you could have sand and rocks mixed together and you pour them through the sieve and the sand is small and it falls through and the rocks are big and they stay in the sieve? That's what your filtration membrane is like. It's like a sieve in your sandbox. So as the blood flows through, the small molecules are pushed out. Okay, so we will look at the forces that push those small molecules out. So you have blood pressure. You rely on blood pressure to push the blood through the glomerulus and push those small molecules out. Remember in chapter 20 when we were talking about MAP, the mean arterial pressure, and on your chapter 20 lab, you had a question about what would happen if MAP were too low, and the answer was that you wouldn't be able to push blood through your kidneys, and your blood would become toxic because you couldn't filter the waste out of it. So here's where that blood pressure is important. If you think back also to chapter 20, we had the HP of a capillary, the hydrostatic pressure. It was 35. So that is in a capillary of your body. And if you need to, look back at chapter 20 where you labeled that. It was the first page of notes from chapter 20. It's a picture of a capillary. We talked about hydrostatic pressure and colloid osmotic pressure. Okay. In the glomerulus, your HP is 60. I'll do a different color for each of these. So the glomerulus has an HP of 60. That's much higher. Remember, HP stands for hydrostatic pressure. So that's the blood pushing against the walls of the capillary. The reason the HP is so high in the glomerulus is the difference in diameter of the afferent and efferent arterioles. See how the afferent is so much bigger? So you have a big input, but a small outlet. So the entrance is really big. It's letting lots of blood in. But the exit is small. So you get this traffic jam in the glomerulus. And this traffic jam increases pressure. So that is how you get a hydrostatic pressure of 60 in the glomerulus, even though out in the rest of your body, it's only 35. Then remember from before, we also talked about colloid osmotic pressure. Remember this? We talked about it in chapter 18 and again in chapter 20. This is the fact that plasma protein attracts water. So there's still plasma protein in the blood in your glomerulus. So we have a colloid osmotic pressure. And your colloid osmotic pressure is 32. So this is pulling in. So your glomerulus has a colloid osmotic pressure of 32. So this is the plasma protein pulling water in. Okay, and notice they're opposite, just like in the capillary you studied in chapter 20. The hydrostatic pressure pushes out, colloid osmotic pressure pulls in. Now in the glomerulus, we have a third pressure. This one is another hydrostatic pressure, but this is hydrostatic pressure of the capsule, and this is 18. So remember this, that catches the filtrate is Bowman's capsule. When that filtrate comes out, it is trapped here. It can't just spread out like it can elsewhere in your body. It's trapped between the glomerulus and the capsule. So Bowman's capsule has a hydrostatic pressure of 18. This pressure occurs because as the filtrate leaves the glomerulus, it is trapped between the glomerulus and the Bowman's capsule. So it builds up and creates pressure. So this is a pressure that doesn't exist elsewhere in the body. This is only in your nephron. So that pressure of all this filtrate building up and being trapped here pushes back this way. So we have three pressures. The hydrostatic pressure of the glomerulus, which is just the blood being pushed out, or the liquid in the blood being pushed out. You have colloid osmotic pressure, which is the protein pulling it back in. And then you have a capsular hydrostatic pressure pushing back in. So we want the net filtration pressure. So this part right here is net filtration pressure. It's what you get if you add all of these up. So you have 60 going out, 32 going in, 18 going in. So if you add all that up, you end up with a net filtration pressure of 10 out. 32 and 18 adds up to 50. So you have 50 coming in, you have 60 going out, you end up with 10 out. That is your net filtration pressure. This is normal circumstances. So under normal circumstances, you will have a net filtration pressure of 10. And if you maintain your net filtration pressure at 10, you will make 2 liters of urine per day. So this is a typical healthy adult, nothing strange going on. Average person makes about 2 liters of urine a day, and you do that by having a net filtration pressure of 10. And we're going to look a little bit more at that net filtration pressure. The Coke bottle here represents your 2 liters of urine per day. Right, so think of a 2-liter soda bottle that you would go to the store and buy. That is about how much urine an average person makes in a day, enough to fill that 2-liter bottle. So we have 3 different pictures here. Remember we said that pushing blood through your glomerulus relies on blood pressure. So the middle picture here, we're going to say is 120/80. This is just a normal average blood pressure. This picture is just our comparison picture. In the picture to the left, we are going to say that this person has low blood pressure. Right, so their blood pressure is below 120/80. we want to maintain net filtration pressure. And keep making 2 liters of urine. Even though blood pressure is lower. So we don't have as much force pushing the blood through the kidneys. So we have to compensate for this. Okay, so remember before we said that elsewhere in your body, the hydrostatic pressure was 35, and then in your kidney, because the afferent is bigger than the efferent, we got our hydrostatic pressure up to 60. Well, now, because blood pressure is lower, that's not 35. Let's say maybe this is 30, right? So you have to do something to still get this to 60, even though you have a lower starting number. So if you compare this picture to the middle one, the middle ones are normal. Compare them and look for the difference. The difference you can find is the size of the afferent arteriole. Notice over here, it's bigger. You dilate it. So when blood pressure drops, and you want to maintain that hydrostatic pressure of 60 in the glomerulus, then you compensate by dilating your afferent arteriole. Okay, notice the efferent arteriole didn't change. It's still the same. So you're making an even bigger entrance, but keeping your exit the same. So you're going to create even more of a traffic jam in the glomerulus, and that'll get that pressure raised up to 60. Now let's look at the other side. This one is showing us a high blood pressure. So the blood pressure goes up. It's above the 120/80. But still, we want to keep that 2 liters of urine per day. So in here, you have an increase in blood pressure. So remember before we said you would have an HP 35. Well, this is higher, so let's say maybe now it's HP 40. Even though this is 40, we don't want this to go up to 65. We want to keep it at 60. Because if you keep it at 60, your net will be 10. That's what we're going for in both cases. We want to keep the net at 10. Because if the net is 10, you'll get 2 liters of urine. So now compare this to the one in the middle. Again, it's the afferent arteriole. See how this time it's smaller? So when blood pressure goes up, you constrict the afferent arteriole. This way you make the entrance smaller. By making the entrance smaller, you have less of a traffic jam. And so you won't raise the pressure as much. Since the pressure is already higher as you're coming in, you don't need to raise it as much. If your pressure were higher coming in and you didn't do this, then you would end up with an HP of 65 instead of 60. And you would end up with a net filtration of 15, and you'd be making more than 2 liters of urine. So this is called renal autoregulation. This is where you adjust your afferent arterial to maintain a net filtration pressure of 10 when your blood pressure changes. So even though you have little fluctuations in blood pressure throughout the day, you're keeping the pressure in your kidneys constant by adjusting that afferent arterial. Okay, these pictures show just the opposite. Now we're purposely going to change our net filtration pressure. So in this one, the one on the left, we want a lower net filtration pressure. Because here the Coke bottle represents your urine. Normally you make 2 liters of urine a day. Now we want to have less urine. Notice it's only a partial Coke bottle. So we want less urine produced. So your body has changed its goal. Instead of the normal 2 liters of urine, your body wants less urine being made. So we have 2 pictures here. This picture is just the normal. This is for comparison. And this picture is the one with reduced net filtration pressure. The stimulus for this, you have 2 stimuli that can cause this. Norepinephrine, which is why I used purple for this, or angiotensin. Angiotensin 2. So hopefully you remember that hormone from chapter 20. Angiotensin 2 is a hormone that raises blood pressure. So if you have norepinephrine or angiotensin 2, let's look at what it does. Compare the pictures. You can see definitely one of the big things you can notice is the size of the glomerulus. It will shrink your filtration membrane. Okay, if your filtration membrane is smaller, then you will make less filtrate. So this means fewer molecules are taken out of the blood. You're retaining stuff in your blood. Okay, and then the other thing, look at the afferent arterial. Compare it to over here. It is constricted. So you also constrict your afferent arterial. This means less blood goes in. So if you send less blood in and you take less stuff out of it, you reduce the amount of filtrate. This means that you are retaining molecules in your blood. So the result of this is you will have less urine and a higher blood volume. And go back to your chapter 20 chart of factors that affect blood pressure. If you increase blood volume, you increase blood pressure. So this is how the kidneys can act to increase blood pressure. And if you look back at that chapter 20 chart, we put about kidneys and urine production. We just said the kidneys make more urine or they make less urine. Well, this is how the kidneys make less urine. Okay. Now, on the other side, we have where you're going to make more urine. So now we have 2 Coke bottles here to represent more urine. Okay, take a minute and go back to chapter 20 and look at your hormones. We had angiotensin, aldosterone, ADH, and AMP. Which hormone makes you make more urine? Which hormone goes here with these 2 pictures? Okay, good. Hopefully you figured out that it was AMP, atrial natriuretic peptide. Okay, here is our normal. Here is our one under the influence of AMP. Actually, AMP is going to increase your net filtration pressure. So when you have AMP, remember AMP is secreted by the heart when it is overstretched. So your goal here is to reduce blood volume. Well, the way you reduce blood volume is to make more urine. The more urine you have, the more stuff you're taking out of your blood. So when you have AMP, you want your kidney to make more urine than normal. So if you look at the 2 ways you do that, look at the size of the glomerulus. See how it's bigger? So you enlarge the filtration membrane. And the afferent arteriole, if you compare it, it's dilated. So that more blood goes in. So by having a bigger filtration membrane, having more blood go in, you will remove more molecules from the blood. So this means you will have less blood volume and you will have more urine. Okay, so there is filtration. Filtration is that first step of filtering the blood where you remove small molecules from the blood. And we looked at how filtration occurs up here, the pressures that cause it. Then we looked at maintaining your filtration when you have fluctuations in blood pressure. And we looked at how you purposely change your filtration in order to increase or decrease the amount of urine that you're producing.